Chapter 11 Gases. We all live at the bottom of a sea of gases called the atmosphere. The most important of these gases is oxygen, which constitutes about 21% of the atmosphere. Without oxygen, life on this planet would be impossible. Oxygen is vital to all life processes of plants and animals. Ozone, O3, formed in the upper atmosphere by the interaction of oxygen with ultraviolet light, absorbs some of the harmful radiation before it can strike the Earth's surface. The other gases in the atmosphere include nitrogen of 78%, argon, carbon dioxide, and water vapor. Carbon dioxide gas, a product of combustion and metabolism, is used by plants in photosynthesis, which produces the oxygen that's essential for humans and animals. The atmosphere is becoming a dumping ground for other gases such as methane, chlorofluorocarbons, and nitrogen oxides, as well as volatile organic compounds, which are gases from paints, paint thinners, and cleaning supplies. The chemical reactions of these gases with sunlight and oxygen in the atmosphere are contributing to air pollution, ozone depletion, climate change, and acid rain. Such chemical change can seriously affect our health and our lifestyle. An understanding of gases and some of the laws that govern gas behavior can help us understand the nature of matter and allow us to make decisions concerning important environmental and health issues. Section 11.1 Properties of Gases. We are surrounded by gases but not often aware of their presence. Of the elements on the periodic table, only a few exist at gas at room temperature: hydrogen, nitrogen, oxygen, fluorine, chlorine, and noble gases. Another group of gases include the oxides of the nonmetals of the upper corner of the periodic table, such as carbon monoxide, carbon dioxide, nitrogen oxide, nitrogen dioxide, sulfur dioxide, and sulfur trioxide. Organic compounds such as methane, ethane, propane, and butane that have small molar masses are also gases at room temperatures. Generally, molecules that are gases at room temperatures have fewer than 5 atoms from the first or second period. The behavior of gases is quite different from that of liquids and solids. Gas particles are far apart, whereas particles of both liquids and solids are held close together. A gas has no definite shape and volume will completely fill any container. Because there is a great distance between gas particles, a gas is less dense than a solid or a liquid and easy to compress. A model for the behavior of a gas, called the kinetic molecular theory of gases, helps us to understand gas behavior. Kinetic molecular theory of gases. Number 1. A gas consists of small particles, atoms or molecules, that move randomly with high velocities. Gas molecules moving random directions at high speeds cause a gas to fill the entire volume of a container. Number 2. The attractive forces between the particles of gas are usually very small. Gas particles are far apart and fill a container of any size and shape. Number 3. The actual volume occupied by gas molecules is extremely small compared to the volume of the gas occupies. The volume of the gas is considered equal to the volume of the container. Most of the volume of the gas is empty space, which allows gases to be easily compressed. Number 4. Gas particles are in constant motion, moving rapidly in straight paths. When gas particles collide, they rebound and travel in new directions. Every time they hit the walls of the container, they exert pressure. An increase in the number or force of collision against the walls of the container causes an increase in the pressure of the gas. Number 5. The average kinetic energy of gas molecules is proportional to the Kelvin temperature. Gas particles move faster as the temperature increases. At higher temperatures, gas particles hit the walls of the container more often and with more force, producing higher pressures. The kinetic molecular theory helps explain some of the characteristics of gases. For example, we can smell perfume when a bottle is open on the other side of the room because its particles move rapidly in all directions. At room temperatures, the molecules of air are moving at about 450 meters per second, which is 1,000 miles per hour. They move faster at higher temperatures and more slowly at lower temperatures. Sometimes tires and gas-filled containers can explode when temperatures are too high. From the kinetic molecular theory, we know that gas particles move faster when heated, hit the walls of the container with more force, and cause a buildup of pressure inside the container. When we talk about a gas, we describe it in terms of four properties: pressure, volume, temperature, and the amount of gas. Pressure. Gas particles are extremely small and move rapidly. When they hit the walls of a container, they exert a pressure. If we heat the container, the molecules move faster and smash into the walls of the container more often and with increased force, thus increasing the pressure. The gas particles in the air, mostly oxygen and nitrogen, exert a pressure on us called atmospheric pressure. As you go to higher altitudes, the atmospheric pressure is less because there's fewer particles in the air. The most common units used for gas measurement are the atmosphere and milliliters of mercury. On the TV weather report, you may hear and see atmospheric pressures given in inches of mercury or kilopascals in countries other than the United States. Volume. The volume of a gas equals the size of the container in which the gas is placed. When you inflate a tire or a basketball, you are adding more gas particles. The increase of the other particles hitting the walls of the tire or the basketball increases the volume. Sometimes, on a cold morning, tire looks flat. The volume of the tire is decreased because the lower temperature decreases the speed of the molecules, which in turn reduces the force of their impacts on the walls of the tire. The most common units for volume measurement are liters and milliliters. Temperature. The temperature of a gas is related to the kinetic energy of its particles. For example, if we have gas at 200 Kelvin in a rigid container and heat it to a temperature of 400 Kelvin, the gas particles will have twice the kinetic energy that they did at 200 Kelvin. This also means that the gas exerts 400 Kelvin exerts twice the pressure of the gas at 200 Kelvin. Although you measure the gas temperature using a Celsius thermometer, all comparisons of gas behavior and all calculations related to temperature must use the Kelvin temperature scale. No one has yet achieved conditions of absolute zero, but we predict that the particles will have zero kinetic energy and exert zero pressure at absolute zero. Amount of gas. When you add air to a bicycle tire, you increase the amount of gas, which results in a higher pressure of the tire. Usually we measure the amount of gas by mass in grams. At gas law calculations, we need to change the grams of gas to moles. A summary for the four properties of gas is given in Table 11.1. Pressure, the force exerted by a gas against the walls of the container. The units of measurements, the atmosphere, millimeters of mercury, torr, and pascal. Volume, the space occupied by a gas. Units of measurement, liter, milliliter, cubic meter. Temperature, the determining factor of kinetic energy and the rate of motion of gas particles. The unit of measurement is the degree Celsius. Kelvin, it's required in calculations. And the amount of gas, the quantity of gas present in a container, its unit of measurement is in grams, moles, and is required in calculations.